Now we go to the Fourier transform. Do I have enough time to go through that? Well, so chapter 20, and the first section is just a very basic overview for integral transform in general. So that let's talk about different kind of transform, that possible transform, the Fourier transform, and there's other transform dimensions. There's a Hankel transform using Bessel function, which we might talk about in the second semester. And the other transform, Marilyn transform, which related to gamma function. But I mean, this is just general information that, and obviously there's Laplace transform that we'll go through Laplace transform later. So, but there's nothing we need to go through section 1. We can go directly to the idea of Fourier transform. Let's see if I can finish that today. So the basic idea is that, so we already mentioned that, we have functions that defined as a finite domain, say, going back to minus L, right? Then there's a function we can use the Fourier transforms or a Fourier series expansion. So whatever function you define over here, you can use the Fourier series. And the Fourier series is if we use the compact series, that's maybe easier. And now it's going back to minus L to L is just n pi x over L, right? And now the coefficients are given by just integrating the function multiplied by e to the minus I over L over the integrate over the period, right? And divided by the normalization, basically saying that we substitute this to here, you should recover C sub n. And the only term survive is the n term because you have minus n. In that case, all the two exponential functions multiply to 1, and to recover C sub n, we integrate from minus L to L, so you need to divide that. Okay, so that is the Fourier series. Now, Fourier transform is basically the thing that you let L goes to infinity. And so the limit of your integration becomes a minus infinity to infinity, so that's minus infinity to infinity. But first, you need to work out how you take the limit, because you have L in the denominator. When you take the L go to infinity, you will kill that the exponential function argument. It become 1, and that you don't get any information out. So you need to take that limit a little bit more careful. And first, we need to change this n. Basically, it's sum over n, right? You take the limit of n. L goes to infinity. First, you change the sum to integration, because now because L is large, so L is large, so you can have a lot more n. Like the density of the integer becomes larger, so that actually becomes an integration. So instead of summation, becomes integration. Integration dn, right? It's sum over n, but n is not a good variable here, because it's combined with the L that we want to to go to infinity. So instead of using n pi, using integrate n, we introduce another variable n pi of L as another variable. So like we usually call it k, but because this is x like a spatial thing, and then the k is a wave number. The text actually use omega, which is fine for Fourier transform in time, but let's just go back to k. Let's just call k defined as n pi in our case, right? So this means that the dn is dk multiplied by L divided by pi. So this, we can change that to dk and multiplied by L divided by pi, right? And now n from minus infinity to infinity means k is from minus infinity to infinity, right? And then you have this c sub n and e to the I. Okay. Now all we need to do now is figure out this how you transform this c sub n, because now you have an L here and you have a c sub n here. So no, that's more convenient. You multiply c sub n with L, which you already have an L here. So L c sub n now tends to L c sub n tends to there's a 1/2 and L to now you can take L to infinity minus infinity. Now you have a minus sign in the same n pi over L, which we call k. No, I haven't done that yet. I haven't done that yet. This is L times n because we have L times c sub n. L times c sub n. Okay. Yeah. So now we substitute this back to here. Substitute this back to here. So fx is now changed to now if you take the limit, you can actually set it to equal sign because we already take the limit. And substitute this here, you have 1/2, and there's a pi here, so another 2 pi. Integrating 1 dk. And then there's an integration of now when you substitute this into here, you don't use x because you already have an x here, you have an x here. So you can change that to like x prime minus I prime dx prime. That's this part. And then all these L, I mean, all these are just except this one, so you need to multiply it. And then dk. Okay, so that's that is the form of the Fourier transform now. Now, what you call Fourier transform now depends on convention. Some people just call whatever this square bracket as the Fourier transform. Then this information, this equation becomes what we call the inverse Fourier transform, because this is your Fourier transform, and then you put the Fourier transform, and then multiply e to the ikx and dk, or divided by 1/2 pi for this formula, then we recover the function. Okay, and so that so the Fourier transform is this square bracket without the 2 pi any 2 pi factor. One convention is that, right, the formula for Fourier transform without 2 pi, and the inverse transform has the 1/2 pi. Okay, so that's one convention. The other convention is put this 1/2 pi in the Fourier transform. So the inverse transform doesn't have 1/2 pi, but the Fourier transform formula has 1/2 pi. Okay, so there's different convention, and lastly is the symmetric convention. You just basically split this 1 over 2 pi to 1 over square root of 2 pi in here, and then put the 1 over square root of 2 pi in the Fourier transform formula. So now you can write the Fourier transform. I mean, you can use a script app. Some people like to use it, or you can use the Fourier transform. To set the text of the symbol that we use. And then later it has this kind of indentation. Using this square bracket. I guess the T just indicates a transform. The transform, Fourier transform of fx is defined as, if you use a symmetric formula, it becomes just the function multiplied by e to the minus x. That becomes the definition. Yeah, get over to almost. Okay, so that's the definition of how you calculate Fourier transform in the symmetric convention. Then once you have this definition, then the inverse Fourier transform is just likewise the symmetric part is 1 over square root of 2 pi. And also this is, after you do the integration, it's a function of k. It's a function of wave number. Okay, and the inverse Fourier transform is the Fourier transform of Fourier transform, the transform as a function of k and multiplied by e to the ikx. Now it's dk. Let me just write it out. This is the inverse Fourier transform formula. This is the Fourier transform formula. Is that okay? So we got this a straightforward generalization from Fourier series to Fourier transform. The difference is that now the function is defined over the whole range of the variable, whatever variable it is. Obviously, subject to some smoothness or some wellness, well-behaved condition that the function fx define over the whole range. Quite obviously, it looks like at least you want f to be 0, tends to 0, but sometimes we actually generalize that even f is finite, especially one simple application is f is just a constant. If f is just a constant, then I don't think I have time to kind of it's just out of time, but we generalize that even f is a constant. We apply this formula later on. We see that that's what we call a delta function. Although delta function is not a real function, it's just something that you put in the integration to do analysis easier. Okay, but normally we will require that this nicely because this integral. If f is not well behaved at infinity, then that function may not exist. So that would be a problem. But sometimes we allow the f is even tends to a constant. Okay, yeah.
What is not
Why is that not? When we change n to k, then, because if you use n, you still carry the L here, and L will later on take the limit of infinity. That make it inconvenient because you don't know the limit n over L. You strictly speaking, this L tends to infinity, everything is 0. Then this thing will be 0, whatever n is. Then that's not good. That you get nothing out of your variable. Everything is 0. So if we define that k, this as a k, basically meaning that if L goes in 0 and you still have finite k, it means that you're using very large n. So basically, this sum is almost filling up all the So this as k goes to infinity, or for finite k, the n has to go to infinity in order to cancel the L, the limit L goes to infinity. So if we define a variable so that you don't need to carry all these limit, right? So basically make your limit more explicit. This limit allow you to take the limit of L goes to infinity in elsewhere, right? To make it more convenient, basically. You can always say that infinity to infinity, any function is just, there's nothing is infinite, right? So always it's a finite domain, and then you go back to doing Fourier series, that's fine. And we do numerical simulation, always have that. So if there's nothing like an infinite, when you do simulation, you always truncate it to a box that you call it large enough, and that when we say we're numerical simulation doing a Fourier transform, actually we are doing a Fourier series, right? It just, when the box is larger, there's a lot more n, or the grid points are a lot larger, then the number of n that you need to sum over the Fourier series becomes large. Okay, and that's the reality, but conceptually, especially doing analysis, is nice to define something that is continuous and then define over the whole range of your variable. Okay, that will allow you to do a lot of analysis using like what we just learned, the complex variable to do integration. That would be easier than a finite discrete sum. Okay. Okay, any more?